The second context involving rates and distance, where we end up needing to use a system, involves one person catching up with another. Right, so in this story, Susie takes off for school at 7:45. She's walking 3 miles per hour. At 7:55, her mother notices she forgot her lunch and sets out after her. Her mother's walking at 4 miles per hour. What time does Susie's mother catch up, and how far have they gone? Right, now there's a trickiness to this problem, and that has to do with the way that we measure time. Right, so our unknowns, they're told us in this question right at the end of the problem, right? They're the distance they've gone and what time it is on the clock when mom catches up. And what are the rules? Well, of course, distance equals rate times time will come into play here. Right, what else? Well, we know that if Susie sets out and walks some distance, and then her mom sets out and catches up with her, they walk the same distance, right? Do they walk for the same amount of time? No, mom starts out later, right? Mom starts out 10 minutes later. All right, let's think about what that means. Right? Well, of course, it's the same time for both of them when they catch up, right? So that means if mom starts out 10 minutes later, mom walks for 10 minutes less. Okay, I think we understand what's going on now. Let's see if we can model this. Let's give the distance traveled a name. We'll call it D. Now, the time when mom catches up, right, that's going to be some clock time. I would really rather not try to do computations with a clock time. I'm going to try to do computations with just a duration, the time that it takes. And I've chosen T to be specifically how long mom takes to catch up. Right, so not how long Susie has been walking. There's one more complication here. I noticed that the speeds are given in miles per hour, but this difference in time is a number of minutes. So I also need to decide what units to use. I think converting 10 minutes to hours is going to be easier, so I'm going to say T is in hours. Right, so that means mom's time is T hours. Susie's time is 10 minutes more. A minute is a 60th of an hour, though. So her time will be 10/60ths more. I can reduce that fraction. T plus 1/6. All right, so they travel the same distance. For mom, I'm going to get the equation D is her rate, 4 miles per hour, times her time, T hours. For Susie, I'm going to get her distance equals her rate times her time. And I think that's it. I think that that's our system of two equations. We're ready to solve this now. Pause the video and try to solve this system. Okay, I think that this is set up for a super duper easy substitution. I'm going to replace D by this thing that it's equal to, and I'll get 4T equals 3T plus 1/6. Distribute to simplify, and I'll get 4T equals 3T plus 3 times 1/6, that's 3/6, which is 1/2. Subtract 3T on both sides, and I get T equals 1/2. Now I can go back to either equation to find D. I like this first equation. D is 4 times 1/2, which is 2. I think I'm ready to answer. Ooh, I'm ready to say how far have they gone. I'm not quite ready to say what time does Susie's mother catch up. All right, so let's see. T is 1/2. That's a half hour, which is 30 minutes. Susie's mother started at 7:55, and then she walked for 30 minutes. So she caught up at 8:25. All right, now I'm ready to answer. The distance was 2 what? Our time is in hours, our speeds are in miles per hour, so the distance is 2 miles. Now, does that answer make sense? 2 miles makes sense as a walking distance. It's a little long, but not crazy long. 8:25 makes sense for a time. It's not super duper late in the day, but it's not just seconds after she left either. I think that this makes sense. So our answers make sense. We're finished.